So now we're moving to intertrial coherence. So Scott talked a little bit about that, and here we're going to see what this corresponds to. So we had these vectors, and we've been ignoring the orientation of the vector. We just looked at the length, took the square, say this is power, and this is all that we were interested in so far. Now there's also some information in the phase. So here we have different trials, and this one, so it's just one window here, for instance. And this one's the amplitude is 0.5, and the phase is 0. This one's amplitude is 1. The phase is 90 degrees. This one amplitude 0.5, phase 180. And here I just put the orientation of the vector. So I normalize the vector, and I just put the orientation. So we take the mean of the square of the amplitude, and we get power. So 0.44 or minus 8.3 dB, for instance. Now for the orientation, we're going to sum these three vectors. So we're going to do this vector plus this third vector, and we're going to obtain one vector in this orientation. We're going to divide it by 3, because we had 3 vectors. And this is what we're going to call the intertrial coherence. Other people call it the phase locking factor. It's exactly the same thing. The same equation. There's no difference. Now let's imagine all of these where they were like in phase. So all the peaks were aligned. So I would have the same orientation right here. And when I would sum the free vector, I would have a length. I would have this one vector plus 1 plus 1. I would divide by 3, and I would have a length of about 1. So it would tell me that in my different signal trials, the brain waves at a specific frequency they have the peaks aligned. So when the peaks are aligned at a given frequency, you have a high value of intertrial coherence. When the alignment is random, you have a value close to 0. This is another representation here. And so here different single trials. I have 3 single trials. I compute the ERP close to 0. This is the total power. And here I have some power increasing in this region. And now this is the ITC. So I have my 3 vectors oriented in different orientation. So when I take the average of these, I'm going to have intertrial coherence relatively low. The length of the resulting vector. Now you can see now they're much more aligned, and there is more in the ERP. The power is strictly identical to here, but the vectors, they have similar orientations. So now I'm going to have intertrial coherence of 0.8. So the intertrial coherence for the classical ERP is 1. Why? Because in the classical ERP, every single trial has the ERP to some extent, and they all have the peak at the same latency. It's not always the case. Is that you can see something in the ERP, like for instance right here, and there's no alignment whatsoever in the single trials. And this is also what Scott was talking about, where he was modulating all of these, showing that you can decrease the power, increase the alignment, and observe some ERP, etc. So it's a complex relationship between the ERP and what happens at the single trial. And the ITC help us to better understand. If we have a high ITC, then it's a true ERP. If we have low ITC, it means the ERP mostly arises from fluctuation in the single trials. This is the formula to compute the ERP. So this is my vector, frequency f time t, trial number k. I'm going to divide by the length of the vector, so I'm going to have this normalized vector. And basically, I just do this average of all these vectors. So these are complex number. I just average these vectors, and I get the ITC. And I look at the length of the ITC. So this is the exact formula that's implemented in EEGLAB. This is an example on real data where when you use EEGLAB, and you can see here there's an increase in power after the stimulus presentation. So this is the power, and this is the intertrial coherence. And there's also an increase in intertrial coherence in this region. Here this is masked for significance, so we see better what's happening. And we can see here but there is more power. So this was two conditions where the subject was attending or not, and we can see for this specific, I think it was an independent component, we had more power at this latency. And we also had more synchronization of the signal trials in this specific condition than in this condition. Now the last thing, the last method, so this is the graphic interface where you would plot the time frequency transform, and it's going to be in a few minutes, where you select your channel or component, and you select your the time limits you want, the number of points you want. You can do frequency padding like we were talking about before. You can use divisive baseline or additive baseline, and you can visualize in dB or in absolute values, and you can use FFT or wavelets, etc. And when you click OK, this is with the default values. It's going to tell you I'm using 3 cycles at the lowest frequency and 12.8 cycles at the highest frequency. I'm estimating 23 linear space frequencies. You can also do log frequencies. And it's computing, and this is what you get. So this is, it puts the scalp map of the ICA components, or it puts a dot if you're computing on the channel. And this is the time frequency decomposition. This is the ITC on the bottom, and the ERSP on the top. And you can change this parameter. You can mask it for significance, for instance. And this is what you get. If you want to publish your paper, you need to check this box, which is called correct for, it's using false discovery rate to correct for multi-port comparison. And we'll have a whole lecture on statistics by David Groupie tomorrow that compared many methods for correcting for multi-port comparison, showing that the FDR seems to be relatively optimal. These are unpublished results. And you see this was the original signal. This is mask. So now we put everything that's not significant, we put at 0. So it looks a bit more patchy here. You can use frequency padding. So this is the pad ratio of 1, pad ratio of 2, meaning that when it extracts this window, is gonna make them twice bigger. And you can see that it's smoother here than here. And here, this is what I told you. I can enter my frequency sequence, 1, 2, 3, 4, 5, 6 hertz, and my wavelet cycle, 1, 2, 3, 4, 5, 6. So it's using, by the way, it's using Morley wavelets by default, although you can use 2 other types of wavelets. And this is what you get, 1, 2, 3, 4, 5, 6. So here I have 6 lines, and I have about 200 time points. And this is my, this is what I usually use. Is I like to plot frequencies in log space because at higher frequencies it's more spread out. So I plot in log space between 1.5 hertz and 100 hertz. I put 65 frequencies log spaced. And then for the number of cycle, I'm going to increase from 1 to 8. So I'm going to use 1 cycle at the lowest frequency. Why? Because at 1.5 hertz, I only want 1 cycle, so I can have some kind of time resolution. If at 1.5 hertz, I use, for instance, 10 cycle, I'm going to need 15 seconds of data. But when as I get higher in frequency, I can increase the number of cycles. So here I increase linearly to 8, and then I cap it at 8 above 30 hertz. Why do I do that? Because most papers, for good reasons or not, for studying gamma, they use from 8 to 12 cycles. So this way, I can look both at low frequencies and at high frequencies. So I cap it at 8 above 30 hertz for this reason. So I can study low frequencies because I have some time resolution. And for instance, for theta, I only have 2 cycles. So I can see some slow oscillation. If I was taking 10 cycles for theta, again, I would need very, very long windows. And at high frequency, I don't I don't need that. So on the single plot, I'm going to be able to look at theta and also high frequency. And if I wasn't doing this cap right here, it would keep on increasing at different frequencies. So I would look at 30 hertz, I might have 8 cycles, but 60 hertz, I'm still going to have 20 cycles. And then it's harder, it might be harder to interpret. That's my personal preference. You can do whatever you want, of course.